Welcome to the video on Design of Distillation Column. I'm Dr. G. Kirtika, Associate Professor, Chemical Engineering, SRM IST. Here we will see an outlay of distillation column, relative volatility, and also we will take a design problem and evaluate the design parameters of height and diameter of the distillation column by a tedious procedure. Distillation column, as you see, it's a versatile equipment which is used for separation in chemical industries. It is used widely in chemical, petrochemical, pharmaceutical and food industries. So it is an equipment which is used to separate the liquid mixture based on the differences in the boiling point. The separation occurs by repeated vaporization and condensation inside the column. Here in the picture, you are seeing the trays which is arranged inside the distillation column and vapor moving upwards and the liquid which scrolls downward and it is separated based on the differences in their boiling points, or it is called volatility. The top section is known as enriching section and the bottom section is known as rectification section. So here we have to estimate the total number of trays which is required to achieve desired separation, and also the feed condition and the feed plate at which the feed enters the distillation column. Here the design parameters are height and diameter of the distillation column. Relative volatility measures the tendency to vaporize one component of liquid relative to each other. It is indicated by alpha. When alpha is 1, it means both the liquid mixtures are vaporizing at the same boiling point. So when alpha is 1, there is no separation possible by ordinary distillation. We need to move on to the rigorous distillation of azeotropic or extractive distillation. If alpha is greater than 1, it indicates that among two components in a mixture, component A is more volatile than compared to component B. Then we can apply a normal distillation column or ordinary distillation column with McCabe method of calculations for achieving the desired efficiency. Higher the alpha, easier the separation, and only few trays are required to achieve the desired separation. Here in this video, we will take a design problem, analyze the problem, and we will solve the problem starting from the material balance to calculation of minimum reflux ratio, followed by the height of the distillation column, number of stages, and also the diameter of the distillation column. To illustrate the design of a distillation column, let us just read out this question. A plant with an annual throughput of 0.06 million ton requires a distillation column to separate a equimolar mixture of methanol in water available at its boiling point. Design a sieve tray column. Find the number of actual stages for operation at atmospheric pressure with a reflux ratio of 1.5 times the minimum. The operating conditions lead to the following data. Overhead product 91.4% of mole of ethanol, residue 1.5 mole of methanol, average liquid density of 870 and vapor density at top and bottom is given. Average liquid viscosity is mentioned. Here we can see that the flow rate is mentioned as annual. So an yearly flow rate of 0.6 million tons has been mentioned, and also the reflux ratio, the purity which has to be achieved in the as the distillate, and the residue composition has been mentioned. And here we also should note that it is an equimolar mixture of methanol with water and the feed enters at its boiling point. So these are the key points from the given data. Moving further again towards the question, the top column temperature is mentioned with the bottom column temperature in Kelvin and the tray spacing. Like we have to design the sieve tray with the spacing of 60 centimeter has been mentioned with the efficiency of operation of each tray as 49%. The vapor velocity which enters the top and the bottom section of the column can be estimated by using the given formula with rho L and rho V is also been shared in the problem. The XY data is given in the problem. If not, alpha values would have been given and we have to calculate and generate XY from the related formula. Moving ahead, let us just analyze the given data. So first, feed flow rate is given on an annual basis, and reflux ratio has been mentioned. It is a mixture of methanol and water. It is present in equilibrium ratio. Water is there at the boiling point. Overhead product is mentioned. Purity of the product. Top column, bottom column temperature with tray spacing and tray efficiency has been mentioned. Now, let us just see the methodology of solving this problem. First, let us just find the feed flow rate in terms of kilomole per hour, which helps us in getting the material balances. Like we have to calculate the bottom product, flow rate of the bottom product, flow rate of the top product, and also the flow rate of the feed from its purity given, reflux ratio, calculations of reflux ratio, from which we can construct a operating line and of the top section and the bottom section. For Meccabe method, you find the number of actual stages, height of the column, diameter of the column, and the optimized diameter. Finding the molar flow rate of feed, we know that 0.06 million tons. So 0.06 into 10 per 6 million indicates 10 per 6 into tons indicates 10 per 3, like 1000 kgs. 1 ton indicates 1000 kg divided by annually 365 days and 24 hours. So we got computing this, we got 6849.3 kg per hour because it is per hour calculation. So now it is a mixture. This feed is a mixture of methanol and water. We need to convert this into molar flow rate. So finding the average molecular weight, we have to calculate equimolar composition. So 0.5 into molecular weight of methanol plus again 0.5 into molecular weight of water. So divide this to average molecular weight with the feed rate per hour to get 273.97 or 274 kilomoles per hour. So this is a molar flow rate of feed. Computing material balance, the overall material balance includes feed is equal to bottom plus distillate, and the component balance include FXF equal to BXP plus D into XD. Here we know F and B and D values are unknown. So here B can be written in terms of D as F minus D, so that here the only unknown is distillate, flow rate of distillate. The flow rate of distillate can be computed. Once you find the flow rate of distillate, as the feed flow rate is known, the feed flow rate of bottom product can also be computed. So we got the total flow rates which enters as feed and which divides as distillate plus residue. Finding the reflux ratio where YF values can be computed from the given XF values, and it can be substituted for finding the minimum reflux ratio. The formula for reflux ratio and the derivation is not dealt here, where the direct formula has been taken to find out R minimum. XD minus YF divided by YF minus XF will give you R minimum, and actual reflux ratio is 1.5 times of R minimum. So the R value is 0.718 has been computed for the given problem. With a detailed discussion on a Meccabe method, first with the given X and Y data, draw the equilibrium line as a smooth curve. Then mark the diagonal line as a 45-degree line joining 0 and 1. Take the intercept values and mark on the y-axis. So join the molar flow rate of residue, molar flow rate of feed, and molar flow rate of the distillate has to be marked on the graph, on the equilibrium line. So from XT, with an intercept, draw a line that forms the operating line of the top section. Then mark the condition of the feed. Then further by which the operating line of the bottom section can be drawn and intersected. The number of stages can be constructed between the operating line and the equilibrium line till it reaches the feed plate, followed by which the operating line changes and the number of trays are constructed accordingly. With the brief discussion of the Meccabe method for this problem, To further proceed with McCabe-Thiele method for this problem, with R value of 0.17, intercept has to be found. Intercept is xt by R plus 1, where the value of intercept is 0.532. So, mark the value of intercept on the graph and draw a line from xt to the intercept. This forms an operating line for the top section. The feed enters at the boiling point, and hence a straight line has to be drawn to cross this intercept line. Then the operating line for the rectifying column can be drawn from the feed point to XB. Thus, two operating lines, one at the top section and one at the bottom section, has been constructed. The total number of stages has been marked by a triangle which has to be started from xt, and a straight line has to be drawn to the equilibrium line with a perpendicular dropout line to the operating line. So the triangles will be constructed between the equilibrium line and the operating line of the top section till it reaches the feed point, and the operating line will shift to the operating line of the bottom section after the feed point. The total number of triangles has to be counted, which gives the total number of actual theoretical stages which is present in the distillation column. With this estimation of actual stages and the height of the column, the number of theoretical stages from McCabe-Thiele calculation was found to be 7, and the efficiency of the plate is mentioned as 49% as per the given problem. Here, since the vapor and liquid are not in equilibrium with each other, the efficiency of the plate will be computed and it will be included to solve the problem or to find the number of actual plates. So now, as per the McCabe-Thiele method, the theoretical stages includes n minus 1, means it includes a reboiler. So the reboiler step has been subtracted and it is divided by the efficiency of the plate. The number of actual stages is been round off to 13, and it is helps in calculating the height of the distillation column. So for 13 plates which is arranged in the distillation column, the spacing between the column has been mentioned as 0.6 meters. So if there were 13 plates, the spacing will be the spacing between the 13 plates will be only 12. Right. So the 13 minus 1 will give you the spacing between the plates, and there are two extra plates which is added, one for the condenser section and one for the reboiler section. So totally it has been multiplied with the spacing of 0.6 meters to get the height of the distillation column. Next is computation of column diameter. Here, as the temperature of the column varies at the top of the column and the bottom of the column, the vapor velocity has to be computed at the top and the bottom separately, and diameter of two different sections has to be estimated. The molar vapor rate N on the top column is given by D plus R, D into R plus 1, which is 253.92 moles, and the temperature of the top is 340 Kelvin, from which the volumetric flow rate of vapor can be computed. Taking R gas constant of 0.082 and temperature as top column temperature with atmospheric pressure, the volumetric flow rate of vapor is 7091 meter cube per hour. The vapor velocity formula has been mentioned in the question, with the density of liquid and density of vapor was also mentioned. The vapor velocity computed is 0.73 meter per second. So now, for finding the column diameter, area has to be computed. You can see the volumetric flow rate of vapor. If it is divided by the vapor velocity, we get area. So, and hence the cross-sectional area is volumetric flow rate by velocity of vapor, which is given as 2.6 meter squared. Once area is known, which is equal to pi by 4 d squared, the diameter of the top of the column can be computed. Diameter is found as 1.8 meters. Similarly, we have to compute the column diameter at the bottom of the column. Here, the variation lies the same molar flow rate with R gas constant, atmospheric pressure, but the temperature at the bottom of the column varies and hence the volumetric flow rate varies. Here, the vapor velocity differs at the bottom of the column with respect to the temperature and hence the vapor velocity also differs. If you divide volumetric flow rate by the vapor velocity, you can find the cross-sectional area, and pi by 4 d squared is equal to area, which gives you the diameter at the bottom of the column. So among the two diameters, the higher diameter will be considered for the design of the distillation column, where 1.9 versus 1.8, we go with 1.9 meter for the design parameter of height for the distillation column. Concluding the dimensions, the number of stages was found to be 13. The height of the column is 9 meters and diameter of the column is approximately 2 meters. The appropriate material of construction has to be chosen with corrosion allowance and the design consideration for design of the distillation column. Reference Chemical Engineering, Poulsen and Richardson, Volume 6. Thank you.